Welcome to the deep dive. We take your source materials and, well, we pull out the really interesting bits.
Exactly. And today, we're looking at a connection that might seem a bit out there at first.
Yeah, I mean, how does the math you maybe learned in class, calculus,
Yeah.
connect with something like farming?
Right. Like, what's the link between differentiation, integration, all that stuff, and, well, growing crops efficiently?
It feels like totally separate worlds.
It does, but the source we're looking at today, it's actually a resource for college students studying differentiation and integration. It draws a really clear line between them.
Okay, so what's the specific focus from this source that caught our eye?
It's about using derivatives. Specifically, how you can use derivatives to track and even predict how fast crops grow depending on the amount of fertilizer you use.
Ah, okay, so not just if they grow more, but the actual speed. I like seeing calculus used for something so, hands-on.
Me too. And the source really drills down on this core idea of differentiation, that it's fundamentally about understanding rates of change, how quickly things happen.
So when you think about crops, it's not just about the final yield.
No, exactly. It's also about how fast they get there, how
Yeah.
quickly they respond. And fertilizer, well, that's a major factor you can control to influence that speed.
Right. So for you listening, our mission here is to explore how this concept, the derivative, gives us a way to really see the speed, the responsiveness of crop growth as fertilizer levels change.
It's about quantifying that how fast question. Imagine a graph, okay? Fertilizer amount on one axis, crop growth on the other.
Got it.
The derivative is basically the slope of that graph at any given point. It tells you, right then and there, how much extra growth speed you're getting for that little bit more fertilizer.
Okay, and that's where it gets practical, right? Because that slope, that derivative, isn't always the same.
Precisely. The source shows how looking at that derivative tells you if adding more fertilizer is still giving you a big boost in growth speed,
Yeah.
or if you're starting to hit that point where adding more doesn't really speed things up much anymore.
The point of diminishing returns.
Exactly that. Maybe at low fertilizer levels, the derivative is really high, small increases give a big speed jump. But then, past a certain point, the derivative gets smaller and smaller.
Meaning adding more fertilizer gives you less and less bang for your buck in terms of speeding up growth.
Right. It helps you quantify the efficiency of the fertilizer concerning the growth rate. The source might show, like an example where maybe after, say, 100 units of fertilizer, the derivative drops off sharply.
So you'd know that pushing beyond 100 units might not be worth the cost or the environmental impact if your main goal related to speed isn't significantly improving.
Yeah, you could potentially identify an optimal range, maybe not for the absolute maximum final size, but for the most efficient rate of growth relative to the input. It's applying calculus to a real-world economic biological decision.
Makes sense. And you mentioned integration earlier, too.
Yeah, the source touches on it. If the derivative is the instantaneous speed, then integration, summing up those speeds over time, could potentially estimate the total accumulated growth. Another angle for optimization.
It's pretty cool how these abstract math tools give such concrete insights into growing plants.
It really is. It shows calculus isn't just theory. It's a powerful way to model and understand dynamic systems all around us. How things change.
Okay, so let's wrap this up. This deep dive really showed how derivatives, a key calculus concept, can model the speed of crop response to fertilizer.
Yeah, it gives you a way to measure that growth efficiency, spot diminishing returns, and make more informed decisions. It's practical knowledge from math.
Absolutely. Understanding that rate of change is vital for optimizing things like farming. Calculus giving us real-world answers.
Definitely. It's not just numbers on a page.
So here's a final thought to leave you with. If differentiation helps us understand the speed of crop growth relative to fertilizer, what other processes out there, things involving change, inputs, rates, maybe in economics or ecology, or even how populations grow, could you analyze using these same calculus ideas? Something to think about.